All right, let's have a look at an example here. We have an adiabatic turbine that received air. So this is an adiabatic air turbine. So this is air is the working fluid. So we have air coming in at 1200 degrees and a pressure of 800 kPa. So we have 1200 degrees Kelvin and T1 is 800 kPa. And the outlet pressure, outlet pressure is 400 kPa. So pressure falls as we go through the turbine. So P2 is 400 kPa. And as a result of the pressure falling, this turbine extracts work. W dot turbine is a work-producing device. The isentropic efficiency for this turbine, which is defined to be W dot turbine over W dot isen turbine, is 86%. So this device produces 86% of the maximum possible device. W dot isen turbine for a adiabatic turbine is the maximum possible work. So this thing produces 86% of the maximum possible work that you could produce with this pressure drop at this inlet temperature. 1200 degrees and a pressure drop of 400 kPa. So what are we supposed to find here? We're supposed to find the specific turbine work, or if you like, W turb, which is W dot turb divided by M dot. We don't have any mass flow rates in this problem, so we can only find specific turbine work. And I also want to find the exit temperature T2. So I want to find the exit temperature T2. How hot is the exhaust coming out of this thing? Okay. Let me put up a TS diagram so we can kind of keep track of what we're doing here. Let's put up a TS diagram. TS. Let's put in our two isobars. So we have our P1 and we have our P2 isobar. So pressure is falling. State 1. So here's state 1. So I start off at a temperature T1 with a corresponding S1. The isentropic turbine moves vertically downwards to a state 2 sub S. And the real turbine has some presumably entropy generation. After all, it doesn't produce it only produces 86% of the maximum possible work. So there's going to be some entropy generation inside of here. So the real device is going to have a positive delta S from state 1 to state 2. So we're going to have a positive delta S from 1 to 2. So the real device goes from 1 to 2 with an increase in entropy. The reversible device, which produces the maximum possible work, moves vertically downwards. Now notice that the real device has a hotter exit temperature than the reversible device. So this is T2 and this is T2 sub S. T2 sub S is lower than T2 because we're not extracting from the regular device, we're not extracting the maximum possible power or energy from the flow. So the real device has a hotter exit temperature than the reversible device. So I'll just write this right here. Note, T2 is greater than T2 sub S. Why? Because W dot turbine is less than W dot from the reversible turbine. The reversible turbine is extracting more energy from the flow and producing more work, so the temperature is falling further for the reversible turbine. Okay? We're going to be calculating T2, and we'll probably calculate T2 sub S as well. okay, T2 sub S. So I'm going to be putting some numbers in here. I'm going to be putting some numbers in here. Needless to say, no, not needless to say, we're going to do this problem assuming constant specific heats. The previous problem we did involving entropy generation that was a nozzle, that was variable specific heat. So maybe we should do a constant specific heat problem here. Okay? We're not going to use any of these S naughts. Not going to use any of these S naughts. Okay, so let's have an assumption section, and then we shall get started, okay? Okay, so I want to find the work or specific work of the real turbine analysis. So I want to find the real work or the work for the actual device. If we write down the definition of isentropic efficiency for a turbine, not a compressor, a turbine, we get W dot turbine divided by W dot isenturbine, okay? Reversible or isentropic turbine. Now, I have the isentropic turbine efficiency, it's 86%, and I want actually I don't want W dot turbine, I want the specific work. Oh, well, okay, I guess we need to massage this a little bit. So W dot turbine is the specific work of the turbine times M dot for the air going through the turbine, divided by W for the isentropic turbine times M dot. The M dots cancel out. That's the definition of isentropic efficiency. Okay, so I want to get W turbine. So this means W turbine is equal to the isentropic turbine efficiency times the specific work of the isentropic turbine. I know the isentropic efficiency. I do not know the specific work for the isentropic turbine, W isenturbine. So I need to find that. Well, how do I find this? Well, let's apply the energy balance to my isentropic turbine. So by the way, this is our system here, both for the isentropic as well as the real turbine. So obviously it's an open system. So let's apply the energy balance to my isentropic device. E balance on the isentropic turbine. So this isentropic turbine, well, let's write out the energy balance. So we got Q dot minus W dot is equal to dE CV dt plus the sum of M dot H plus PE plus KE summed over all outlets. And then I got the same thing summed over all inlets, okay? Now this is an adiabatic turbine, so this is 0. There's only one form of work, and that's turbine work, or shaft work if you call. So this is W dot shaft. So it's producing shaft work, that's what the turbine's doing. It's got a propeller in there. No change in energy within the turbine, it's steady state. And I don't have any information, well, let's have a look. I don't seem to have any information on any changes in height or any changes in flow velocity at the inlet and the outlet. All I have are temperatures and pressures. I got no flow areas, I have no M dot. So I am going to neglect the kinetic energy and the potential energy terms. So I'm going to write delta PE equals delta KE equals 0. Also, I'm going to say steady state as well. So this is steady state. We're told that it's adiabatic, so I don't need to put that down. So that's gone, and these are gone. And I get W dot and I'm going to call this W dot shaft. I'm going to call it turbine work. And it's also for the isentropic turbine. So I'm going to get, I guess I'll write it right here. W dot isen turbine. There's only shaft work and it's by the isentropic turbine. So I'll call it W dot isentropic turbine. So I get W dot isen turbine is equal to m dot H1 minus H2. If I divide by m dot, I get the specific work. W isen turbine is equal to H1 minus H2. And if I assume constant specific heat, I get CV T1 minus T2. Okay, oops, CP, sorry, CP. CP T1 minus T2. I have temperature T1. Okay, I got temperature T1. I don't have temperature T2. By the way, this temperature T2 here and H2, let's go back to our TS diagram. Is this right? Remember, we're working on the isentropic turbine. State 2 for the isentropic turbine is actually 2 sub S. 2 sub S. That means isentropic. So I am going to put a sub S on all the 2's here. So put a little S here and put a little S here. Okay? Isentropic. S1 equals S2 sub S. Okay, getting a little bit compressed there. That's what that's for. Again, look at your TS diagram. For the isentropic device, we're going from state 1 to state 2 sub S vertically down, and S1 is equal to S2 sub S. Okay, so I need to find T2 sub S. Process 1 to 2 sub S is isentropic. So that's isentropic expansion in the turbine, the reversible isentropic adiabatic turbine. 1 to 2 sub S is vertically down, so S1 is equal to S2 sub S. So I can go, for constant specific heats, I can go to a property relationship. Let's have a look. Let's see if I can pull out a property relationship for constant specific heats. Okay, here. Oh, we don't need these anymore, at least not for a moment. Let's see if we can find that table that contains, what is it, 6.2? Ah, there it is. I think that's it. Yes, table 6.2. Isentropic processes. Variable specific heat, there's the S naught stuff. Constant specific heat. T final over T initial is equal to pressure final over pressure initial, K minus 1 over K. Let's use this. Let's use this to calculate T2 sub S. Let's use this to calculate T2 sub S. T2 sub S over T1 is equal to P2 over P1 K minus 1 over K. And that's from the constant specific heat isentropic property relationship. To do this, I need K, the ratio of Cp over Cv. So I guess I need to look up some specific heats here. I am told to evaluate Cp and specific heat at 1,000 degrees. So let's see if we can find, in our table. Let's go here to specific heats for air, IGB, property tables. Cp and K for air. This is table B10. I only go up to 1,000 degrees, that's why I did it 1,000. I see K is 1.336. So I'm going to write, never mind, Cp and K evaluated at 1,000 degrees Kelvin. I think I'll write right over here. K evaluated at 1,000 degrees Kelvin. What was it, 1.337? 1.336, 1.336. 1.336. Oh, do I have the right camera on? Let's have a look. I need to turn off the share. So K at 1,000 degrees is 1.336. K evaluated at 1,000 degrees Kelvin is 1.336. And that's from table B11, B10. All right, let's calculate T2 sub S. Let's see, that's going to be equal to T1 times P2 over P1, K minus 1 over K. T1 is 1,200 degrees, and my pressures are 800 and 400, as I recall. So T1 is 1,200, and the pressures are 800 and 400 kPa. Pressure drops through the compressor as we're extracting energy. So 1,200 degrees Kelvin, and then I have P2, which is 400, and I have P1, which is 800 kPa. The units cancel out. And then I have 1.336 minus 1 divided by 1.336. And I find a T2 sub S. T2 sub S is 1,008 degrees Kelvin. 1,008 degrees Kelvin. So let's go over here to my TS diagram, and I can actually put some temperatures in here. Maybe one temperature. So this T2 sub S. So this is 1,008, and this is going to be in Kelvin. So this is T2 sub S, 1,008 degrees, okay? Presumably the real turbine, which has irreversibilities, won't get all the way down to 1,008. It's going to be somewhat hotter because it won't extract all the same energy, okay? Okay, so now I have T2 sub S. Great. So, I need Cp. Oh boy. Cp. Well, remember we're going to evaluate Cp at 1,000 degrees, so I guess I better look that up. (1,000 degrees for air, 1.142. 1.142 kilojoule per kilogram to green Kelvin. So Cp at 1,000 degrees, 1.142 kilojoule per kilogram degree in Kelvin. And that again is from table B10. From table B10. Let's make sure I got the right one. Yeah, 1.142. Okay, great. Check. Okay, 1.142 kilojoule per kilogram degree in Kelvin. Temperature T1 is 1200 degrees, and T2 sub S is 1008 Kelvin. The Kelvins cancel out, and I get kilojoule per kilogram, and I get the isentropic work for the turbine is 219.3 kilojoules per kilogram. 219.3 kilojoules per kilogram. So the isentropic turbine extracted out 219 kilojoules per kilogram of flow. So now I got the specific work produced by the isentropic turbine. 86% isentropic efficiency, 219.3 kilojoules per kilogram, and I get the work of the real turbine. The work of the real turbine is equal to 188.5. 188.5 kilojoules per kilogram. 188.5 kilojoules per kilogram. Okay, so let's write these results down. The specific work produced by the actual turbine. Irreversible turbine is 188.5 kilojoules per kilogram of airflow. Note, the reversible device, the one that produces the maximum possible work between the same pressure limits, W isen turbine is 219.3 kilojoules per kilogram. So W turbine is less than the isentropic turbine work. The real turbine produces less power than the isentropic turbine. Let's calculate the actual outlet temperature. The actual outlet temperature for the real turbine T2. We've already calculated T2 sub S. What was that? 1008 degrees. Let's calculate T2. Let's apply the energy balance to the real turbine. Actual turbine. So I apply the energy balance, steady state, no heat transfer, single inlet, single outlet, no changes in kinetic and potential energy, and I get W dot turbine is equal to M dot H2 minus H1. Let's make sure these subscripts are right. H2 minus H1. So for the real device, we're going from state 1 to state 2. The isentropic device was 1 to 2 sub S. That's why in the energy balance for the isentropic device, at state 2, I had a 2 sub S. But the real turbine goes from 1 to 2. And of course, this implies W turbine is equal to H2 minus H1, which is CP T2 minus T1. Now, I have W for the turbine. It's 188 kilojoule per kilogram. I have a specific heat, and I also have T1, so I can solve for T2. So T2 is equal to T1 minus, let's see here. No. Yes. So let's see here. W turbine. Oh, I think I forgot the negative sign here. I did. There is a negative sign right there. Forgot the negative sign from the first law. Sorry about that. Let's see. So I get T2 is equal to T1 minus W turbine over, over CP. So divide both sides by CP. Take the T1 over on the left-hand side of the equation and flip the equation. And I get T2 is equal to T1 minus W dot turbine over CP. Okay? All right, now I have W dot turbine, I have CP, and I have T1. Let's plug in. Let's see here. T1 is 1200 degrees Kelvin. Minus W turbine, 188.5 kilojoule per kilogram. CP, we already looked CP up. What was that? Oh, what was CP? I guess I erased it. That was 1.142 kilojoule per kilogram degree Kelvin. 1.142 kilojoule per kilogram degree Kelvin. The kilojoules and the kilograms cancel out, and the degree Kelvin goes on top. And I have, let's crank it out. Let's see here, 188.5 divided by 1.142. And I get 1,034 degrees. Actually 35 degrees Kelvin. 1,035 degrees Kelvin. So T2, 1,035 degrees Kelvin. Box it up. Let's put this on our TS diagram. So T2 sub S was 1,008 degrees, and T2 is 1,035 degrees. So notice the real turbine has a hotter outlet exhaust temperature. Why? Because W dot for the real turbine is less than W dot for the most efficient isentropic turbine. Therefore, the outlet energy or enthalpy is going to be higher for the real turbine than the isentropic one, simply because less power is being extracted. In theory, I don't mean to get extreme here, in theory, if the real device is so irreversible, I'm guessing its isentropic efficiency were 0, then in theory, the outlet temperature could be equal to the inlet temperature if it's not extracting any work. So for an extreme case would be a turbine with an isentropic efficiency of 0. It produces no power. The outlet temperature, T2, would be equal to the inlet temperature, T1. Not much of a turbine, but is definitely an illustration of an extreme example. An extreme and a generality that real turbines will have a hotter exhaust temperature than an isentropic turbine. Okay, you could do the same thing with a compressor for this kind of a problem. So you'd have a different definition of isentropic efficiency for a compressor. You would still be applying the energy balance. You would still be looking at an isentropic process, 1 to 2 sub S, to get an isentropic compressor work. So compressor problems are very similar to turbine problems, except that you're going up the TS diagram. You're starting here and you're going up. You're increasing pressure, and your definition of isentropic efficiency is flipped, okay? Similar sort of problem involving a compressor. You'll see examples of isentropic turbines and compressors in your notes and in the textbook. All right, take care, ladies and gentlemen.